Diego Clar. He's going to be presenting on Total's latest generation production HPC. He was introduced a little bit this morning by our local CEO, Vincent. So Total, or I'll go ahead and hand it over to Diego so he can present on our production machine.
The mic is okay? Okay. So hello, everyone. So I will talk about the new system we have just installed 1 year ago in Total. So first of all, what do we have such kind of system? I think all of you are already aware of the main usage of such a system. First of all, of course, is seismic processing and imaging, as everyone does. So that represents more or less around 75% of the load of the system. The other main usage is reservoir simulation that represents around 50% of the 15% of the usage of the system. But more and more, we have artificial intelligence working on the system. Here we have 3 examples. The first one here is about automatic classification of microfossil. That is to say that during the drilling of the well, we extract some cores and we analyze and we do biostratigraphy on that to have the age of the rocks. And for that, we have to recognize and to count the different microfossil here, you can see. And now we are able to do that automatically on the system using AI. This is one example. The other one is more classical, let's say. It's here. So it's about seismic processing and the first break pitching. That also should be automatized directly now with artificial intelligence. The third one is about velocity model building here. And more we use to better estimate the structural pattern, let's say, of the Earth. We use AI approach to construct this velocity model. So let's go on the spec of the system. So first of all, I'm going to talk about hardware. So the node in itself, we have around 558 nodes. Each node is composed with 2 IBM processor Power 9, plus 6 NVIDIA Volta V100 GPUs, with NVLink in between the GPUs and in between the CPU and the GPUs. And each node has 500 gigabit of memory. The whole system is consuming very few electricity. We are around 1.4, but that is really the maximum when we put all the clock at the maximum on GPU and on CPU. Let's say on a day-to-day usage, we are more around 1.1 megawatt. The other part is, of course, the interconnect between all the nodes and in between the nodes. So in between the nodes, as I said before, we have an NVLink, 100 gigabyte per second NVLink between all the GPUs and between the GPUs and the CPUs. And that is very useful for us to be able to give enough to eat, let's say, to the GPU through the CPU. In fact, I'm going to talk about development after, but we have developed a dedicated approach to feed the GPU in terms of data to treat. It's a kind of LIFO approach, so last in, first out approach, with a compression made directly for one part on the CPU and for the other part on the GPU itself. The other part of the network, of course, is the InfiniBand network. So we have a EDR, double EDR network 2 times 100 gigabit per second. Last piece of the puzzle is the storage. So we have a single scratch file system of 50 petabytes. It's a Lustre parallel file system, and we achieve bandwidth of 1 terabyte per second. So this is the results, well, not the results, but this is the continuation, let's say, of the global history of high-performance computing facilities and systems in total. So we start in the 80s, and we are going on. So we have installed the first Pangea in 2012. It was a pure CPU-based system, and in 2015, we had the second part of Pangea, Pangea 2, still on CPU system, and now we have Pangea 3, mainly based on GPU and Power9 system. So yeah, those numbers are the numbers in June 2019. So yeah. So as I said, to use this hardware, we had to focus on the development, because we had to adapt a lot of our software to be efficient on the system and on the GPU itself. So for that, we use different products. Of course, we use CUDA from NVIDIA. We use PGI from NVIDIA. Let's say where we don't need so much performance linked to the hardware itself, we use OpenACC and OpenMP. And we use MPI from IBM to be able to use the GPU Direct exchange. So in terms of development, we all know the sequence of classical code, let's say, sequential code. We used to deal with parallelization and parallel code. And the first approach was with GPU to just to put some directives, some OpenACC directive, and that is, let's say, a naive approach. It works in terms of results, I mean, but not in terms of performance. So we are to change the algorithm itself, well, let's say the instruction more than the algorithm, to be able to do at the same time to cache, let's say, the communication by the compute on the GPU. So once you have transformed your code source, you can use CUDA, you can use OpenACC. What is important behind is to have made this transformation to have the real performance. So excuse me, we're on. Okay, so what allows the system all the effort we spend in optimization, parallelization, and so on? So the idea, everyone I think knows about this slide. This is the one from Henri Calandra for decades now. But this is very important. That is to say that the idea behind all this system and the growing computing power is to solve more physics and with more physics, let's say, in the equation. So this is what we want to do at the end of the day, to have less approximation and better accurate results. So here, for example, you have example of what we can do, what we are able to achieve with Pangea 3. So we are able to have a multi-scenario approach. That is very important because, of course, our geoscientists had in mind a lot of scenarios to test, but they don't have enough computing power to do that. And just giving them faster algorithm and faster supercomputer, they are able to do more and more multi-scenario approach and statistical approach of the, let's say, the decision, de-risking more and more the exploration and the production, because we are doing more and more seismic imaging during the production. So here we have an example. This is a comparison on the same field, let's say, between the kind of image we had in 2007 with data acquired on a narrow azimuth way using a WEM algorithm software. So it took about 21 days to have this kind of image. And here, below the salt, we cannot see anything. So now, with the wide azimuth acquisition, applying a reverse time migration, and only 2 days with the new system, we can see over there exactly what happened behind the salt. And that is really the idea. The idea is, with new algorithm, using more physics to have better image. That is to say that to be able to take better decision and faster decision. So that's why we are focused on R&D to develop new algorithm on the one end, but on the other end, we have people in R&D dedicated to test the new systems, different systems coming from all the HPC world, and to be able to understand how our algorithm could be adapted to the system and which system is the best one for our algorithm. So here is several other examples. So for example, taking into account more bandwidth of frequency, we can see here that we have to multiply by 80 the computing power needed when you just multiply by 3 the frequency you want to achieve. And of course, more and more L-stitch approach compared to the acoustic approach to have a better, let's say, delineation and more physics. And at the end, so if you count what I've told about in the beginning, excuse me. So we have 80% of our system used for seismic imaging, around 15 used for reservoir simulation, but we still have 5%. And those 5% are more and more used for, let's say, the other branches, what we call branches is in total, that is to say, refining and chemicals, and I don't remember the third one, but doesn't matter. Let's say that we do more and more CFD on the system, more and more molecular modelization, and more engine combustion. So at the end, I think that just to answer the question that was asked to Vincent this morning, that what will be the more and more, let's say, useful in the future and which will use more and more computing power will be molecular modelization definitively. And I think this is the end of my talk. Thank you very much.
Thank you, Diego. We have a few minutes, about 3 minutes for questions while we're queuing up the next talk.
When you were comparing the WEM to the RTM,
Yep.
how much difference is there in the preparation of the data between those two processes? In computer
In terms
time.
of human time spent to prepare the data, you mean?
Yes,
It's more or less the same.
it's about okay.
Yeah.
Thank you.
Yeah, one in the middle here.
I see that you changed from your architecture from CPU to GPU,
Yeah.
and also you implemented some compression to hide to make your the data transfer faster. What are the challenges from geophysics point of view? Like, are they okay with the output comparing with the CPU?
Yeah. The idea is to have the same results at the end. I mean, for the same algorithm to have the same results. So of course, this is the first thing we check when we port all our codes on the system. And the way we compress is a lossless compression. So we have the same results at the end.
There's one in the back over here.
Yeah, do you find any specific advantages in using the IBM Power architecture over Intel x86?
Yeah,
And,
definitively. I mean, the main difference was the NVLink between the CPU and the GPU that allows us to deal with the memory very easy, an easy way to deal with the memory. And at the end, from what I remember, just if you compare an x86 node with the same number of GPUs and CPU to ours, I think the difference was around, depending on the algorithm, but between 10 and 50% in terms of performance.
do you find that it limits your software choices at all, or are you guys mostly rolling your own?
Excuse me?
Do you find it limits your commercial software choices at all, or are you mostly rolling your own stuff?
No, we
internally?
develop our own software.
Okay. Thank you.
Yeah, more and more. Yeah, both. Yeah.
Very short question.
Yeah.
Can you say a few words on your I/O workload? How much time you spend doing I/O operation while doing your, RTM?
Talking about RTM, just RTM?
Yeah, just RTM.
Okay.
Yeah.
So RTM in terms of I/O, the idea is effectively in the first part of the RTM just to read the data, and because when I talk about RTM, I talk about least square RTM, in fact. So each part of the RTM is not so I/O intensive, but at the end we have to gather all the sub-image, let's say, in the final image, and that is very I/O intensive. So for that we have developed, as I said before, a dedicated compression algorithm, and we have part of the system we can use as a server I/O. That is to say, a server really dedicated for I/O. And in fact, this is a dynamic approach to have the number of servers, I/O servers needed compared to the compute, let's say, nodes we use.
Hey, we got time for one more question. Chen, I'm going to give you opportunity for one question.
Our CPU
Yeah.
supports the PCIe Gen 4 first, okay?
Yeah.
So is that a reason you choose the CPU too? Because Gen 4 obviously has much better I/O throughput potential,
Compared to what?
the typical Intel x86.
Okay, but we are using NVLink between the CPU and the GPU.
Oh, so it
That
doesn't
is
matter.
much more better
Okay.
in terms of bandwidth and in terms of latency.
Okay, okay. Thank you.
Okay, thanks for your questions.
Thank you.